Okay, is there nobody in the back row that's got their name tag? Arno, good job. Nobody else? You guys are resisting. Ah, hi, John. Lab session. But the reason that we're really excited about this is that if you work through this lab and carefully, you will understand all the material that we're trying to do. You will also review for the final exam, and you'll have kind of done everything. So it's a little piecemeal, question by question by question, and using of the apps that I think is really going to promote learning in a way that I don't think we've actually been able to do before. So I'm kind of also looking for your feedback. We'll do that at the end of the year about this. But I feel that this structure is a resistivity of the rock convey. When we think about ease of passing a current, if a rock is resistive, does it pass current easily or not? No. So resistive is telling us something about how easy it is to pass current. And what is the survey that we're actually doing? A DC resistivity, which involves putting a current into is to work with the app as far as just a background. This is the same app that you're going to be using in the lab this afternoon. And the first thing that we're going to do is to kind of look at the currents. Get them all on here. So let's just look at a single current. So we're just going to have an A electrode, and we're going to put it, let's say, in the middle, and we're going to look at just the electric potential have a full suite of these guys. So here's the A electrode, here's the B electrode, so the current's kind of going in like that. And then I can have two potential electrodes. One is N that's connected to the positive side of the voltmeter, and one is N that's connected to the other. For now, we just want to kind of look at what happens here. You have some options as to what you want to have for the resistivity. So we're just going to look at the resistivity of 500 ohm meters. And then we can plot a number of things. So you can see up here, we can plot the So this number is like 100. So it's got a positive value up here in the yellow, and then it goes down towards 0 out here. So it's a pretty bland type of thing, but that is the potential in the ground. What we're interested in is looking at the electric field. So the electric field, so if I've got a potential, let's suppose in this case it actually looks like this. If I do the contour lines, right, so it's high here and it decreases as we go away. So I looked at this. Larger as we go that way. So if you think about going uphill, the negative gradient says it's going like this. So these lines here are sort of the negative gradients of the potential, and that's the electric field. So the electric field is the force. So if you put a charge, then there's an electric field on it. It's like a force that's going to push. So if we looked at the electric field, we see it looks like that. So the electric field is pointing out like this. A circuit with some voltmeter in here, get current, resistor. Then we got current that was in here, and we had voltage is equal to I bar. Okay. When we work in the continuous format, so this is like I, if I change that, I get I is equal to V upon R. If I am in continuous format, I get equal J is equal to sigma E is equal to E So if I now plot the currents, have they changed direction? Yeah.
How does J relate to I?
J, so J is current density, so it's amps per meter squared. I is the total current. So if we had a little interface here with some area A, and we had some go out in and out. Okay, so now what happens if I take this system and I put in two currents? So what are we now going to expect the currents to do? Anybody? John? Quentin? Person, just think about, okay, so suppose I had that, what would the currents look like in the ground? So this is the whole way of using an app anyway. So let's go, so I'm going to put an A electrode at -30, B electrode. Okay, so now we're going to look at the currents. So do you all have a mental vision of what it is you're expecting to see? How the currents will flow if you have a dipole. And the electric potential that we see looks like this. So it's that positive thing over this A electrode where we've got current going in. And then if we've got something coming out like this, so this is like having a negative Q. And so that means that potentials are going to go like this. So if I now plotted what was going to happen, here's A electric, here's a positive. what's going to happen in the Earth. So now there's actually a couple of apps that you have. One's called the Cylinder app. That's what I first looked at. Now we're going to look at a 2-layer app that allows us to do the following. What we're going to do is try to figure out, okay, how am I going to get the resistivity of the Earth by doing something crazy, which is just putting in currents here and then measuring, the electric potential. So I showed you yesterday right? So we went through that kind of last time. Where we were is then trying to figure out, okay, we can't actually do that experiment in practice. I don't know how to just measure, I don't know how to just put a current in. I need to have 2 currents. So I need to fill a circuit. And then also, I can't measure a single potential, I have to measure a potential difference, right? So the basic experiment is one where you have 2 electrodes for the battery, and you've got 2 other electrodes for the and so then that means that the V for AM is equal to rho I over 2 pi r. If I had another potential out here, let's say at electrode N, then that would, I'd know what the potential of this is. It'd be just the same as that. The only thing that is going to change is the distance, because I'm now at a distance r a. So that tells me the distance between potential electrode N and current. So if I have a negative current here, so it's like a minus Q, then the voltage, remember, was at this opposite sign, and so these numbers here are going to be. So I can use superposition. I can just add all of those guys up, and then I get a resistivity. I get a potential difference then that looks like this. So it's just the same form as we had before. It's rho times I times this geometric factor that's just related to the distances between the various electrons. Okay, so that's you're going to put electrodes in at various places. So here's current A, sorry, and B, and then you put an amp here or an N here, however you like. Collect in very different different geometries, and then compute what the voltage difference is, as well as then the apparent resistivity. Let's just do that. So now we're going to apparent resistivity. So the resistivity is obtained by, well, we take these numbers here, subtract them, that gives us a delta V, and now we put that into this formula, and then we get the resistivity. In this case, because the Earth is uniform, we actually get out the resistivity. Thanks, Josh. Okay, so is that starting to make some sense? Yes.
So, on the formula,
Yeah.
when it says delta V M N,
This whole thing here is just G. So this is delta V is equal to rho I G. That okay? Okay, so this is actually important. Yeah, go ahead.
Sorry, this is one general question. Why would we get a view by hand? Doesn't it just use the top of this distance and just get one complete circuit rather than producing like that? If you're pumping in currents from
Yeah.
one and then getting out from the other.
Yeah, so we're pumping in currents here, and they're flowing from here. But this whole region is just a uniform. I don't know, how thick a layer do we want? This is 40 meters, 5 meters. So we can adjust this. There's this bar here, slider bar, that tells us the thickness of the layer. So if I right now it's at 5, so let's leave it at 5. Okay, what sort of a resistivity would you want? So you're talking about making it more conductive, so four in the back, black hair. Yes, your name is? Zenica? Okay, what's going to happen? Well, we're going to put a conductive layer in. What? Yeah.
Current's gonna go through the path of least resistance.
Okay, so the current's going to go through a path of least resistance. That's good, and it's going to go through the layer. And anybody else? Question? More current is going to go through here?
Yeah.
Yeah, I think that's pretty good, but there might always be some small amount of current that's coming through there. If you had a name tag, I'd give you a star. It's kind of like a virtual star. Do you have a thing? I'll give you a star for that one. You don't have one either? You guys are missing out. It's going to be worth it. Okay.
Just quickly before you change that, is there any current going through the purple layer? It's hard to see because of the color.
Through here?
Yeah.
There is a very small amount. Yeah. So it's kind of like we had just talked about. You know, it does bleed through. If I made this even more conductive, then I right? So what do you have? I mean, what's your basic equation? That's kind of it, right? Is equal to some source. That's your equation for all your groundwater stuff, right? Okay, what's the equation for DC resistivity? It's exactly the same. You have hydraulic conductivity, we have electrical conductivity. You have head, we have potential. If we measured the potential difference, then we actually got out the resistivity. So in a half space, we got exactly the right number, right? It was 500 ohm meters. What is going to happen to this case where we now have this higher, lower resistivity region at the surface?
Through, so it wants to be that top layer.
Perfect. So this is actually a point of resonance, I think, for you, because you're thinking about flow, okay, water, which is good, okay. But if you've got, let's suppose you've got two layers, one with one hydraulic conductivity, one with another, then you still might expect to see some flow down through the bottom here. So anything that you got for, let's say, an effective conductivity, okay, is going to be something, a little bit of this, a little. We're going to use the same formula that we used for the homogeneous Earth. We're going to plug everything into that, but then we're going to call it like, okay, that's an apparent resistivity, which means the resistivity of a uniform half space that we give rise to. Yeah, Annie?
So despite them having super different resistivities when calculating
0.55. So it's higher than 0.1 and it's lower than 500, which is kind of what we would expect. Okay, so let's do an example that's not quite as extreme. It'll help a little bit. So let's change that resistivity that we had at the first layer to 10. Okay, whoopsie. We're going to change that to 10 ohm meters. Information out about what is happening as a function of depth. And the answer to that is yes, we can, and there's also an intuitive understanding about why that is. So let's first look at an example where I'm going to take my layered earth. So you can think about this in a thought process. I'm going to put my layered earth, and I'm first of all going to put my A electrode here and my B electrode here. Okay? And I've got some then what's going to happen to the currents under the ground? Yeah. Yeah, so it's just going from one to the other, right? So it's kind of doop, doop. So just sitting here doesn't even kind of get down to Allen, right? So if I do that, my apparent resistivities, so I had a row 1 of 10, so I got 10 ohm meters, and this is at 500. You can see my seeing is something kind of close to what that near surface overburden is. So let's now go and expand things. I'm going to introduce a word for you. It's the type of experiment that I've got. So every experiment's got different geometry. So this one has got an A electrode here, a B electrode here, an M here, and an N here. And all of these are spaced by a uniform distance of A. And it's called a Wenner array. whole length here, okay, is like 10 meters. Let's just kind of keep that in perspective. So we had something here that was 5 meters thick, right? And if I have an array here that is 10 meters, then my parent resistivity, maybe I'll do it over here. So this is going to be my length. That's 10 meters, and my parent resistivity is, can you read that from there? Yeah. What's going to happen? Well, we just showed some examples of that, right? So if I've got electrodes that are sitting right close together, you know, the currents just kind of go in like this. If I pull them farther apart, electrodes are going. Yeah. So Arno. Compared to the thickness, we're still actually more influenced by what's happening here. And then we can continue on with that and make, let's go all the way down to 30. So now at this point, we've got more current that's flowing in, and my parent resistivity is at 61. If I have a resistivity of 10, but L is really small, I basically pick up just this resistivity of this upper layer. But as L gets larger, then I gradually am going to pick up, and maybe if I got it far enough, this would actually come up to be 500. And where we are, we're kind of in here, even though this was 60 meters, yeah, I'm still only 50 or 60 ohm meters. I've got quite close. So this thing here, that's called a sounding curve. And if we go back work together, then the currents kind of go like that. There's some that go in here, but in this case, the upper layer was 100 ohm meters. So it's 100. It was 100 ohm meters over 500. And when I'm really very close, I'm just sensing that upper layer. If I spread them farther apart, then my apparent resistivity gets up to 135, and you can see where the currents are flowing. And if I go to even farther apart, I get more current that's flowing through here. That the resistivity of the layer was really 10 ohm meters or something, that might tell you something more about what's there.
Okay.
So here's sort of a summary then of what are called sounding curves. So you basically start particular geometry of electrodes. In this case, we used something that looked like that. I'll talk about that next time. It's called Schlumberger rays. It's basically the same kind of thing. We start off with a particular configuration, and we successively expand about a point. Yep.
Like a real life situation, what are like typical?
Basically, the distance between the two farthest electrodes. And it doesn't matter whether they're currents or potentials. Now, as far as how they're used in sort of in-mine situations or on the surface, for geotechnical work, people often use arrays that are maybe 50 meters or 100 meters long, in which case you might be able to see down 30 meters or something like that. But they have done experiments, in fact, I was involved in one, where the electrode spacing was actually 1,000 kilometers. And then we got down to close to 300 kilometers into the Earth. So. Into this point, that's kind of what you're up against. Every data that you acquire has got some information from everything. Okay, we didn't get quite as far, but we're okay.